Good evening, everyone. Thanks for coming. I just wanted to make a couple announcements. We're going to be having a pretty busy fall for meetings, so wanted to get the dates on your calendars. Our next meeting will actually still be in September 25th. It's a Thursday. And that is a talk from Dr. Bjorn Schuler about artificial intelligence in health. And then our next talk after that will be in October 17th, back here at Mann Hall, on convolutional beam forming for joint denoising, dereverberation, and source separation. Plus, we'll still be having our yearly winter meeting where we have EMBS host it. So we'll be quite busy. And I hope everyone comes back out to join us. So I'm going to let Richard here introduce our speaker.
Okay, so thanks everyone come here and in person and online. We're glad to continue our dear distinguished lecture speaker series. We have one this year. We have booked four distinguished speakers. We already have one in June. So this is Dr. Batt from Nokia North America is our second one. And we'll have, for just as Chris said, we have another two coming up. So it's my honor and the pleasure to introduce our distinguished speaker from IEEE Communication Society, Dr. Majit Batt. Excuse me, my pronunciation of first name. So Dr. Batt is a senior staff research scientist at Nokia USA, and an adjunct research professor at the Trinity College Dublin, Ireland. And he has held various positions at the University of Glasgow, UK, Trinity College Dublin, Ireland, and Fraunhofer Heinrich Institute, Germany. Okay. So he has written many papers, more than 100 peer-reviewed articles, and it contributed more than 150 filed granted patents in cellular network. So Dr. Batt, he has a very long list of awards. For the sake of time, I just mention some important ones. So he has won several awards for his research and innovation, including the Nokia Inventor of the Year in 2022, IEEE Region 4 Outstanding Research Professional Award in 2024, last year, and the Maria Curie Best Inventor Award in 2025. So he also served Industrial Program Chair for IEEE WNC 2023 and 2024. And Dr. Batt is a senior staff research scientist at Nokia USA and adjunct professor in the Trinity College Dublin, Ireland, just to say that. So he also served as associate editor for IEEE Communication Magazine, IEEE Open Journal of the Communication Society, and IEEE Open Journal of the Vehicle Technology. He is a senior member of IEEE and IEEE Communication Society Distinguished Speaker for 2024, 2022, and 2025. And he also Industry Program Chair for IEEE WNC 2023 and 2024. So after the talk, if the members and the interesting, we'll have for dinner with our speaker in our close restaurant here. If interesting, we can, or any other after talk, I think maybe you have some thing like to talk to the speaker for more details about the technology involved. So with no further ado, Dr. Batt, the stage is yours.
Can you hear me? Good. Thank you, first of all, for inviting me for this distinguished lecture talk. Uh, it took some time, but finally we got it right. Yeah, so today I'll be talking about a very important topic in the sense that a lot of people are curious about 6G. So now we are, because we start looking at these Gs even 5 years before when actually things happen. But I don't think that there is any better time to talk about 6G by industry point of view than this time, because we had our first meeting about 6G last month. So that was the official starting of 6G. So anything before that was more of a VN. And I was just talking with Richard, and he said that we already had a talk last year, and when we asked someone that what is 6G, he said, I don't know. So no one knows. But now we know. So that is the difference. And that was pretty much very recent. Last month, we started working on that. So it's good that we do have a lot of community from industry. So it will be easy to communicate what I'm trying to say. So this talk will be a bit different. I will not going in the details of one particular topic. It will be very broad topic. I will try to cover that how these G's kind of thing work, because a lot of people, they just hear about many myths about different generations of cellular networks, but because normally in conferences we don't get much information from the industry speakers. So it's academia, and academia start talking about G's, as I said, 10 years before actually it happened. So this is something we can't do. So that is the main contribution for this talk. So that is a brief outline for this talk. I will give some introduction about the topic, then what is the timeline for 6G, and in particular, we'll talk about machine learning. So the good thing is that 6G will be the first generation of cellular networks where we do have AI embedded right from the beginning in the system. Up to 5G, we had nothing coming out of AI, in spite of so much of literature. So you will see thousands of papers talking about AI doing this and that. We had nothing. And in your practical networks, there was nothing. So 6G will be our first opportunity to use AI to build systems. So that is the key. So then I'll go on with this overview of machine learning in 3GPP. 3GPP is the main organization that standardizes cellular networks. So basically our networks, they are built on the rules that are defined by 3GPP. And it is a consortium of all the companies, vendors, cellular network operators. So before we start building something, we need to agree on certain standards. And this is the platform where we do that. And so when I say that we just started with 6G, so that means that 3GPP started discussing 6G last month. So that was the first meeting, and then we have another meeting. So I'll show that timeline. And finally, some applications and challenges that we face as engineers while we are building systems. So I'm not talking about research. There is much in research, but our challenges are a little bit different. So you already heard a lot about me. So thank you, Richard, for that. So I will not read this through, but just briefly that I'm part of Nokia Labs as a senior staff research scientist, and I also do have an academic position, which is an adjunct position. And besides that, for my voluntary work, it's I'm part of IEEE in the capacity of IEEE Concept Distinguished Lecturer. And just a warm up. So this slide has nothing to do with the topic of the talk. I just like to show this talk just for people to get some interest that this is the place where I work, Bell Labs. And this year we are celebrating 100 years of Bell Labs. And if you look at the history of Bell Labs, it started in 1925. So it's not all about telecom. So if you look at the whole thing, it used to be a research company. So almost every decade we had something remarkable. So we had this electron diffraction in 1937. Then if you are a communication engineer, then of course you know about this Shannon's landmark work. That came in 1948. Transistor was invented in Bell Labs. I don't know if you know this. Then laser was another invention coming from Bell Labs in 50s. In 60s, there was a lot of work in satellite domain. So Telstar was one of the key achievement. And in 70s, we had Unix operating system and C language. So both are, now I think many people don't know that they came out of Bell Labs. So now everyone uses that. Then later on, we had a lot of work in electronics, optical networks, lasers, and in the 20th century, the focus was more on cellular networks, and then we had this MIMO and stuff. So if you look at the whole picture, this 100-year of research, it's not all about communication. It used to be about science, fundamental science. And as a result, I think now we have 10 Nobel Prize from Bell Labs in 100 years, which is quite a lot for a research company. So we are not academic institute. We are a research company, and 10 Nobel Prize is a lot. So that is more about the history, and that was just a brief intro to the place where I work. So now let's move to the main topic. Evolution of cellular networks. So again, I will just use this slide as a building block. So everyone talks about these Gs. So this one generation, usually it is 10 years time. So generation means that we start building networks with some new technologies, and then we just go with that main technology. Obviously, the systems evolve with time, but usually for the next 10 years, we don't do any kind of revolution. So it's more of an evolution. So we try to fix things. We don't try to bring something which is completely different. And that is one problem, I guess, with AI, that it came at a point when we were kind of done with 5G around 2017, 18. And at that point, normally we don't take new technologies because we are close to finalizing our things. And usually, if you see that we had first deployment of 5G in 2019. So it means that system need to build before that. So we kind of finalized release 15, which was the first release for standardizing 5G around 2018. And that was without AI. And after that, we tried to do something about AI, but there was nothing major that we could do. So now for 6G, right from the beginning, we know that the next G will be based on AI. So that is why we call it AI native network. So now right from the beginning, we knew that AI will be part of the system. So we designed our systems keeping in mind that AI will be behind the system. In 5G, it was not like that. So we tried to just plug in AI solutions wherever it was possible, but we couldn't really change things. And I'll show later on this. So what happens with these Gs? So usually when we go from one generation of networks to the next generation, so we keep on using whatever we had before, but we try to improve on that. So in 2G, which was GSM, if you remember, quite a few years back, it was just about for voice, nothing else. And in 3G, broadband data came. And so what we did, so we tried to improve previous version, which was voice. So if you remember, in 3G, voice was very cheap as compared to 2G. And broadband was the new technology. And broadband was expensive at that time. So what happened in 4G? So we got higher data rates, which already came in 3G, but now we try to improve that. And now low cost data. So we try to reduce the price of data. So that is why 4G was more about data. It was not 3G, because at the time of 3G, it was so expensive that people didn't really buy that. And unfortunately, that has happened with 5G. So 5G is not a commercial success because we have the technology, but we don't have the use cases. We don't have the users. So it's not a problem with the technology. It's just that we couldn't find the right use cases. Now people don't care. We solved the issue with these higher data rates in 4G. So in 5G, people don't want to have more data rates for more money. We can provide them, but they don't want because they don't need. And that is something that we need to correct in 6G. So it's not just about the technology that you keep on improving technology, but if no one needs it, then it's not going to be successful. And that is what happened with 5G. And now in 5G, we need to bring new use cases. And that is, in 6G, we will try to bring new use cases. But more important is that the use cases make sense to people. In the end, this is a business. If you don't get money out of business, then it's not success, even if your technology was great. And this cycle shows that what happened with, particularly with 5G, but this happens with every G. So if I can use, so do we have a laser or something with that I can use to point? Otherwise, I can just use this. Yeah.
Yeah, there you go.
Yeah, that's compared.
Yeah, so this works, but okay. So this, I think you are familiar with this hype cycle. So this is what happened with 5G, that this was early hype about 5G and early developments up to 2019. And as I said, that in 2019, we had the first deployment of 5G. And we improved on low band coverage, more data rates, everything. But actually, that was just an improved version of 4G. There was nothing much into that. So then after a few years, then this is a trough of disillusionment, that then the businesses, they started thinking that, okay, how we could make money? This is not going to work. Just saying that this is better, this is improved technology. That's not going to work. And then we had COVID issue. And so that was pretty bad timing in that sense. In post-COVID time, it was even difficult to sell this 5G thing. So that was the time here, around here, at this point. And then we are coming back to the realities that we need to find new use cases, slicing, private networks, AI/ML, edge computing and stuff. So, and most of the Gs, they go through this. But that was pretty much the case with 5G as well. So let's more talk about 6G now. So this timeline started, so as I said, that in 2018, we had this release 15, and that was 5G. So we were done with 5G at this point. Though deployment happened in 2019, but for us as a 3GPP standards researchers, we need to complete our work by this time. So then after that, it was deployment. So that was the 5G standardization. Then we tried to improve in release 16, 17, nuts and bolts. And then at this point, we started to go in this 5G advanced standardization, which you may know that because Gs, they are separated by 10 years. So usually after 5 years, we have something which is like 4.5G or whatever you call it. For 5G, we just said that it's 5G advanced standards. So next three releases, 18, 19. So we were trying to fix 5G. So there was nothing about 6G, whatever the academia was saying. And then release 20 started, and that is what I'm saying. So this is, here we are at this time. And you see that this is exactly the time where 6G starts. So here in this phase, 6G concept and requirements that start from around 21. 3GPP was not doing anything with 6G. It was more about academic work. In academia, you will try different concepts and you will see that what makes sense. And then at this point, industry will start thinking, okay, what are the key technologies that we would like to implement in next generation? Forget about what academia is saying. There are many technologies which are very much hyped, but they never come to the standards. So basically, we never implement them. So this is exactly the time where industry starts thinking about 6G. And this is exactly where we are. This is the end of 25. So by the end of release 20, this 5G standard will be done. We won't do anything with 5G after that, even not the nuts and bolts. Anything which is not finished by this time, we will just roll it over. So now after this point, everything is 6G. So that is how the timeline works. So now, what are the 6 key technologies that we identified few years back? So I will not say that this slide is very recent. And there is one reason that why I'm bringing this slide, even if it is a few years old. So a few years back, we thought that these are the 6 key technologies that will be part of 6G. So that was a kind of vision. So we thought AI/ML, artificial intelligence, machine learning, air interface, that will be key technology for 6G. We need new spectrum. Of course, every G needs it. So we need higher bands as well for higher data rates. And then we had network as a sensor. So sensing is a key use case. So that was envisioned a few years back. And we have nothing about sensing in 5G. So that would be a completely new thing. So that was envisioned. And then we need to improve RAN core convergence and specializations. So as I see that, I just want to keep this talk at very high level. So I will not go in the details of these things, that how this, so RAN is more about access networks over the air, core is what we are doing behind. So we wanted to have more flexible networks. And then we wanted to have extreme connectivity. Extreme connectivity means that there are still a lot of areas where we don't get good connectivity. Sometimes in the tunnels, for example, we don't have good connectivity. In some rural areas, we don't have connectivity. So we want to have good connectivity. And what are the technologies that could provide us? And satellite could be one of them. So again, satellite is nothing new. For many, many years, people are talking about satellite, but is it a mainstream technology? Still not. So that was one of the vision as well. And then security and trust. And you all know that with the AI, we have a lot of issues with security and trust. So we need to solve that, because if we provide a lot of new technologies, but they're not secure, we are not going to implement them. 3GPP is a very secure system. Anything which is not secure, even if it is very good, we don't implement that. So that is the key. And now let's see that. So AI in wireless, so where we would like to use it. Why we would like to use it? There are a couple of reasons. First, either we want to improve the performance, like data rates, improve the latency, connectivity, anything. Or we want to reduce complexity. That is more related to the signal processing thing. Sometimes we do have algorithms available which perform very nicely, but they're so complex and they take so much time that we can't really use them. And that is the reason sometimes we don't use them. We use suboptimal solutions because they can provide us the solutions, at least in the time scale that we want. And that is the second reason for using AI, because AI can provide those solutions a bit fast. So that can be the second reason. And then the third reason is that with AI, with wireless networks, the thing is that the things change very fast, particularly if we have a high mobility users. So you just take a turn around a corner and it's a completely different wireless environment. So you really need to change your communication parameters. And AI is very good in that kind of sense because AI can predict that. All other systems, they are reactive. Something happens, then you will do something. But in AI, that is a good thing, that you may predict that this user may take a turn, so what I need to do. And that is the core feature about using this AI for wireless networks. And let's try to predict what will happen and then take proactive action instead of just waiting that what happens. So wide range of applications. So people thought that, okay, we can use AI everywhere. And I think most of you will agree that there was a time in last 5, 6, 7 years that if you go to any academic conference, 80% of the people are solving every problem with AI. But and that is what everyone thought. So we had these many use cases. Okay, you can solve everything by using AI. But then things don't work like this. So later on, we have to do some research about the practicality of the solution, that providing better performance is not enough for implementation of a solution. Sometimes it's that much complex that we don't really need that solution. So we need to think about that enabling feature. And that is exactly what we do in 3GPP. Sometimes some very good technologies, we never implement them because they were too complex. So companies, they never agreed on that. So it's not just about the performance, which is usually in academic papers, you will see that, okay, my scheme is providing better performance than this other scheme. So this is very good, fine. But the assumptions that we are making, they make it very simple. When you try to deploy it, the complexity of implementing this solution is so difficult and so much that companies, they never agree on that. And in 3GPP, you have to agree. It's not that, okay, some companies are saying that I want to implement this, so I will implement. But in the end, the systems, they have to work with other systems. So that is the role of 3GPP. And in spite of that much hype, so that was my starting statement for this presentation, that no aspect in 5G has been designed by AI. And partially it was the reason that we kind of standardized 5G in 2018. And by that time, AI was not that matured. And now it's 7 years ahead, and we believe that now maturity level is much different. So let's look at, so first we looked at this timeline for different releases generally for different Gs. But now let's look at that, just focus on AI ML, that how AI ML entered in the picture. So that was 2021. And at this point, we started working with the AI ML. So there was some work on network automation and AI ML. But still, again, just to clarify that this is not about 6G. So this work is not about 6G. This was just starting to think about implementation of AI. And then in the next release, then we have next generation RAN that came 22. And this release 18. So now at this time, we are into release 20, which is at this point. So with the passage of time, we kept on increasing the studies that are using AI/ML. So we were getting ready for 6G. So we took 5 years to get ready for 6G, because at 2021, the companies, they already knew that 6G will be highly influenced by AI. So we just need 5 years to think that what we need to do in 6G. And then in 25, we started. So 5 years was the time just to think. And then 6G started. So this is the actual work. And this will produce some standards. And why we need standards? There are 3 key players in wireless networks. We do have network operators, which provide you service. Then we have network vendors like Nokia or Ericsson, for example, which provide you equipment for your networks. And then we have device vendors, which provide you your handsets. And all 3 of them, they need to work with each other, because if device algorithms, they're completely different from the network algorithm. So it's like 2 entities talking with each other. And if they don't agree on any language, there is no way that you're going to understand each other. So that is the role of standardization. That we need to agree that, okay, when I send some signal, this is how you perceive that. And this is a role of 3GPP, that we come up with some standards that everyone has to implement. So it is about interworking with multi-vendors. And one other important thing here is that, which is also kind of, it's new for academic community, that in 3GPP, we never standardize algorithms. So most of the time when people talk about AI/ML, they're talking about different algorithms. They're talking about the performance. But in 3GPP, we never standardize algorithms. We standardize that what we need to run an algorithm. You can use whatever the algorithm you would like to have. So for example, a device vendor can use any algorithm that it wants. And we don't need to know that as a network vendor. But we need to know that what your algorithm will provide us as output. How it gets that output, it is never implemented, or it's never standardized in 3GPP. And most of the companies, they will never show you your algorithms. So that is an important thing here. So let's see that what is the role of standardization here. So you have entity 1, this is your handset. This is what we call UE, user equipment. And then you have a network equipment here. So as I said, that if a device vendor is implementing algorithms to improve performance at this entity 1, you can even do in 5G. Though 5G was not built for AI, but if you want to use it inside the device and network doesn't need to know about that algorithm, then just implement that and improve your performance, because you're not making any difference to the world outside. The outside world doesn't even know that this solution came from AI or it was a non-AI ML solution. So that you can always do. Same for the network operators. And that is what we were doing in last 5-6 years. Without touching the standards, try to improve your algorithms. But then there is a limit, because if the other entity cannot communicate with you, then how much you can improve. So we did improve both on the UE side and on the network side. But there was huge limitation that these 2 entities, they cannot communicate. They don't assume that this functionality is built by AI. And without that assumption, it was very difficult to implement something. So what is next? So now we have what we call level Y, that these are 2 entities, and they need to know that other entity is implementing AI algorithm or not. And here we need to have 3GPP standards. And that is something that was missing in 5G. We didn't have that. So here we communicate between two entities, UE and network, through some signals, and we help each other. But we don't send any data, we don't send a model. And in this third level that is called level Z, so these two entities, they are not only communicating with each other, but they may send AI/ML models or the data related to the machine learning model over the air interface to help each other, to run one functionality. So these are the three different levels. So again, for the first level, you don't need standards, just implement whatever you want. But for the other two, you need help from the standards, and you cannot build them without help from the standards. Okay, so then things became even more complicated here. That what kind of model? So now, as I said, these are the 3GPP specifications between this UE and the network. So we have three different cases. The first case is that your AI/ML model is sitting here on the network side. And then what device can do? So it is here in the UE. And then this is your AI model. It's at the network side. So what UE can do? So UE is the entity that is measuring different channels. So UE provides its information to the network, and then the network implements AI/ML model. So it means that the data that network needs, that is coming from UE. So they need to agree that what the UE will send, in what format you will send, how to interpret this data on the network side. So here, model is at the network side, but UE has to help network. Then we have device-sided. So device-sided means that the device will implement the AI/ML model. So model will be in your devices. And then network has to help device to implement that. So network has to provide some control. Okay, now you should do that. If you're going to in this direction, so maybe you are changing your cell. So maybe this ML model is not good. So maybe use this. So network is not having this ML model on its side, but it's giving all the instructions to the UE that how to use that model that you already have. Because UE may have more than one models that it can use. And network has always more information about the whole thing, because network has information not about one particular UE, it has information about all the UE. So maybe you are going towards a crowded area. Your UE doesn't know that, but network knows that. So maybe network will tell you that you should maybe use this algorithm. That may suit you better. And that it will tell by using some signals, and that needs to be standardized. And then the most difficult case is this is two-sided. So in two-sided, what will happen that one part of the algorithm is on the UE side, the other part of the algorithm is on the network side. So actually, without communicating between two entities, this cannot be even implemented. Because you do one part on UE side, then you need to communicate and let network know that what I did, these are my results. So now you do your part and complete the whole thing. And you can imagine that how much communication and coordination these kind of cases need. And we do have examples of this case where 3GPP is already standardizing. So it's not that it's just a VN, it is a reality. Okay, so 5G Advanced is the key stepping stone towards AI native in 6G. So as I said, that we started preparation of 6G 5 years ago, and that was what we were doing in 5G. So mostly we were having proprietary AI/ML solutions, which was level X that I showed in one of the previous slide, which means that you don't need to communicate, do whatever you want on your side. Standardized features for network automation. So some solutions came for network automation, but without communicating. And then in 5G Advanced, we brought some use cases. So we started studying. We didn't really bring any solution, no standards, but we started studying that what are the key use cases where we can implement. So in one of the slides, as I showed that 5 years ago, people thought that we can do everything with AI/ML. This was not the case. So we need to think that, okay, what are the key problems that you can solve by using AI/ML? And that is what we were studying in last 4 or 5 years. Enhancements for data collection, how you will collect data. So you know that for AI/ML solutions, the key thing is data. And until 5G, we never implemented systems that collect data. So how you will collect data? In the end, these are your handsets, UEs. They have to collect data. But if we don't tell them that how to collect data and what to collect, then they are not going to collect it. So you're not going to implement your thing. So that is something that was done in 5G Advanced. And then generic support for AI/ML solution a little bit. And that brings us to this 6G AI native system. So what is AI native? AI native means that right from the beginning of the standards, we know that 6G will be, AI will be part of the 6G system. So we build our system keeping in mind that the algorithms will be AI based. So think about a few years back, your KPIs could be different. We never thought KPIs like what is the training accuracy, because we never trained system in wireless. So what is the false alarm? What is the hit rate, or all those parameters which are related to AI? We never thought about them, and they are not part of wireless world. But now in 6G, they are part of the system right from the beginning. In 5G, we never had them. We never thought about them because there were no ML algorithms. But now we do have. So we need to think about training speeds, UE capabilities, how fast you can train, how fast you can infer, all those things. And they will be part of the standards. And this is what we call AI native. That we know that your algorithm is, it depends on AI. So I will not really go in the detail. This is just for the motivation that whatever I'm saying is not a story. We do have use cases where we are working on that. So for instance, this is the first use case, that best beam prediction. We always do that in 5G, but we never used AI/ML. Now in 6G, this is one of the first use cases that we believe that we'll be using AI/ML, and this will be standardized. So we already have first set of specifications for this particular use case in release 19. And here what you are trying to do, so you're trying to predict the best beams based on a limited set of measurements. So instead of, usually we do have a lot of beams, and that means that the UE needs to report all those beams, and then your G0B will let you know that what is the best. But the first use case was, okay, let's not feed back all of them, because they are like 32 or 64. And it's a lot of communication, and that is not really useful data. That's overhead. So let's just feed back a part of that, maybe 8. And then use some AI/ML on the G0B side, and that the G0B can infer about other beams without actually getting them. So it's just a picture, but let's say that you feedback this beam, and this beam, and then all these white beams, they are predicted by the AI/ML algorithm. So you don't send them, but you have it. So that was one of the use case that will be part of standards. And even better than the best beam selection optimization. Again, this is something we were doing even before, but now this will be done with the AI/ML. So we need to figure it out that what happens between these UE devices, how these UEs select best beams. So maybe conventionally what we will do that, okay, each UE will measure something and it will say, okay, this is a beam where I get best results and I will select that. But maybe this selection of that beam is not good for the whole system because too many users, they are selecting the same beam. So eventually you will not get the best results. But as a UE, you don't know it. The network knows it. So it means that if we have some kind of AI/ML based solution, network can let you know that maybe this is not the best thing. You measured something and you believe that this beam will give you the best throughput. But I can tell you that this will not be the best for you. So basically you are helping UE to make a better decision. So that was another important use case. And now we do have an example of what I said, two-sided AI/ML. So here a part of ML system, ML model is on the UE side, the other part is on the G-Node B side. So what here we are doing that UE is measuring some inputs, and then normally it will send all those measurements to the G-Node B, and then G-Node B will make a decision about CS. So this is what we call CSI prediction. But this is a lot of data again. So that consumes a lot of useful resources. So what you can do here is that instead of sending all that, you can use the AI/ML model on the UE side to compress those measurements. And then you send all those, this compressed code word to the G-Node B. And then on the G-Node B, you have a decoder, which is again AI/ML based. So that will decompress that code word and you will get the same measurements, but you don't send them. So implementation of this encoder and decoder. So that is AI/ML based. So that is another use case that has been worked on. And that is two-sided. Again, CSI prediction. So that's another use case that instead of predicting all the beams, you observe some and then predict others for the future. So you can use AI/ML for this. AI/ML positioning. So all of us, we know that our UEs, they are providing us very good positioning nowadays, but we can still improve that. So that is a next case where AI/ML has been standardized. So we are working on this use case for last 3-4 years, but now in the one of the coming release. So AI/ML will determine that positioning. So obviously it helps a lot to improve your performance. So that's another key case. And finally, this is AI/ML enhanced mobility. So when you move from one cell to another cell, so what is happening conventionally in handovers? So your signal strength from one particular cell is decreasing, you move to another. So you are going, maybe your channel is improving for another cell. And system will look at all those measurements and it will take a decision. But as I said that sometimes we do wrong decision, and you might have experienced these, that your call drops. So that usually is the result of that bad decision. That system couldn't understand that system thought that maybe this cell is better for you, but actually it was not. And here we believe that AI/ML could be very helpful because AI/ML can predict much better that what next action you are going to take. So in which direction a user is going. If you are going in this particular direction, maybe we should start handover. And how AI/ML will learn? Because we do have a lot of data. Because most of the time, if you're going on a particular route, most of the cars, they will take the same turn. So if something happens with one person, it will happen more likely with more than one person. So network has all that data. So network can predict that this is the place where most of time we have issues. So let us try to predict that this user is going toward that direction. So maybe I need to hand over to another cell before actually you go in that particular area. So that is a prediction about your mobility that that will be made. So you can already see it here that maybe this is the building that is creating a blockage here. So if we already have predicted that this building is there, so usually we have issues here. So when this car is going towards this direction, we can already start a handover. We don't need to wait that it already reaches here, then the signal is already bad, and then we start doing something. So we don't need to be reactive. So that's another key use case. And then we had some other studies about, as I said, that data collection is a key part. And that has been extensively studied in 3GPP, that how you would collect data. Without data collection, there is no AI/ML. And there are many issues with this collection of data, because even privacy and trust, they're one of the key issues here, that you cannot fetch data from the UEs without their consent. And so it's a much bigger framework, but here, how continuously you get data, because in the end, measuring a lot of parameters and then sending back to the G node B, it takes a lot of network resources. So you don't really want to keep on draining all those resources just for collecting and sending data. So you need to have a proper framework that what to send and why to send and what you will do. So maybe sometimes we don't need it, so don't send it. So all those kind of things are very important for implementing AI/ML solutions. Okay, and then there are some other use cases. I will not really go in that details, but energy saving is a key use case that has been studied for AI/ML, because you can switch off some of your cells. If no one is using them, then maybe you can switch it off. And here again, intelligence is important. We can do it even without AI/ML. You just observe that there are not many users connected to a particular cell, and you just do that. But again, that is a reactive. Here, what we are saying that maybe we can predict that no one will use this particular cell at this particular time. And why? Because we have a data from many UEs for many, many days. So maybe over the highways, how many people will use cellular networks in the midnight? Not many. And most likely you will repeat those patterns. So if somehow we could predict that, we can switch off some of the cells and then some other cells can take over. So it doesn't mean that you will not get your connectivity. You will still get your connectivity, but because we turn off some of the base stations, then network is very energy efficient. So you are not wasting a lot of energy. Then we have this load balancing, which is again very much related to this energy saving and mobility. Okay, so now one other thing that that is important as a user of AI. So sometimes on your mobile handsets, you will be running AI and ML algorithms, but your devices, they don't have the power to do that. So what you will do? So these are very kind of futuristic kind of things. Maybe at the moment we don't feel that, but the way things are going, this will eventually happen. That you want to do something, some AI/ML app is installed on your UE, and you want to get some information about something by using AI/ML model, but the model is so heavy that you cannot get your results. It's like many years back when we just started this era of internet. So we used to browse and then we keep on waiting that our website will open. Now you don't want this with the AI/ML, that you used AI/ML, but the algorithm is so heavy that you're waiting that when my result will come. So one thing that we can do here that, okay, this is UE. So it can split this AI/ML which is running on this mobile between itself and the network. So maybe it can perform some function, some kind of inference, which is partial. And then it sends some results to the network. And the network, because network has more capability, it has more power. So it can perform that rest of the inference and send the results back to the UE. And that could be faster than running everything on the UE, because UE is energy limited device. It may drain all of your energy for your device. So it's not good even for the UE. But now the issue is that how to decide that what to send. And that goes over the air interface, and that has a cost as well. So now you have to think that what is bad? Processing everything on my device, or doing a little bit of processing and then sending it to the network, and then the network does the rest of the processing, and then network sends me everything back. So what is more energy efficient? There is no clear answer for that. But at least in concept, it means that in some cases, one will be better, and in the other cases, the other will be better. And then you have to decide that what is the better solution. How much to process locally? It will depend on each use case. In some cases, maybe a particular application is very, you have security issues with that. So user doesn't really want to send it to the network. In that case, okay, whatever the thing is that you would like to process locally, because you don't just want to send it. But network needs to be ready to help you, at least from the network side. So that is one of the use cases that we tried. Then you have a little bit different case where AIML data distribution and sharing over 5G systems. So in this case, everything is on the end device, but you need a lot of data, model data from the network. So what could be an example of that? So again, this is an application thing. So this is not related to the network itself. So you as a user, you go to a certain place, maybe a mall, and you want to run a particular AI app for something. Maybe you just want to scan something and you want that every kind of data about that thing comes. And for that, you want to use some kind of AI. So here, one solution is that like our apps, just download all kind of models. But in the end, how much you can do? You cannot really do that. So then this becomes like an on-demand service that you are going towards a mall, you let network know that I'm just entering this network. And then the network predicts that you will need this AI/ML model. And it automatically sends it to you before you actually use it. But then once you are out of mall, somehow you need to remove that part, because otherwise your device will be full of AI/ML models. And this is something you don't want. So if you enter the mall and then you scan something and then but a model is not here, in that case, you contact network, ask network. It's like a web thing that you ask network to send me model. Models are heavy. It may take some time. So you're not going to wait for a few minutes, just that model downloads and then you apply. It's not like an app. ML models are much heavier. So it will take some time, and then it's coming over the air interface. So there is some kind of prediction that we predict that what UE will need, and then we already download it over the UE device, if UE allows that. Of course, this is again trust thing. So that is what you have here, that this is a cloud and here AI/ML model. And again, you need some kind of information over this air interface. Without standardization, you can't do that. It's not like conventional app. And finally, this distributed federated learning, that maybe there are many UEs, none of them have power to do any processing for a particular algorithm. So maybe they can combine, and with the help of network, they can train a very good model that all of them can use later. And again, network is in between. So network needs to get ready for getting all that data to process it and send it back. And then again, just keep in mind that there will be trust issues. So there will be security. So that you have to account for in the network side. So that is always important thing. And finally, okay, so you all have AI/ML models everywhere, but then still you need a network management thing. So this is a core network, some AI/ML models, this is radio network, some AI/ML models. But what if some of your AI/ML models in radio networks, they ask you to take a particular decision, which is good for doing something, maybe improve your throughput, but maybe this is not good for something else. So you could have conflicting AI/ML models. One model is suggesting you to do this, but the other model is suggesting you to do something else because you optimize them separately for different functions. So for that part, you need this network management, that there must be an entity that should resolve those kind of issues that, okay, if we have those kind of conflicts, then you should do that. Because there is no person sitting there and making those decisions. You need to have framework, some procedures that if these kind of conflicts happen, then what you will do. So this is very key here. And finally, before I just end today's talk, it's a very small thing. And usually I present it because many people, they don't know what is standardization research. So we do have academic research, which everyone knows. And then we have implementation engineers, which again, everyone knows that we implement algorithms. But then what these standardization guys are doing. So that is something that I can show you here with an example. So this I just included to tell you that we also write papers. It's not that we're just doing talks. You don't need to really go in the details of this slide because that was not the main purpose. Here, the main thing is that we do performance analysis for a particular use case, as you saw in some of the previous slides, like beam management, positioning, everything. But our work starts after that. Okay, you have a good algorithm that can provide you very good positioning results for the UE, but how you would implement that? So these are different entities for the network. So you could have G node B CU, central unit, and then you G node B DU. So how you implement my algorithm? So this place is closed. So for the training part, so this is usually we have lower layers at this G node B DU level. And this is UE. And UE is measuring some radio parameters. And it needs to send those parameters to the network, and then network will take a decision. So obviously, you would like to send these measurements to the entity which is closer to you, because then it will take much less delay. So it is more efficient in terms of delay. But the problem is that the framework that we have defined for these measurements, so the interface that we have, so usually those measurements are defined to be here. So these measurements, they never go here conditionally. So we can do two things. Either we can define a new interface that sends this information here, and then we can have machine learning model here. Or the other way around is because this information is already going there, so why not to put your machine learning model there? So these kind of decisions, this is again just one example. So we have papers which I have included in this slide. So these kind of decisions, they are based on practicality. They have nothing to do with performance analysis, but they are big part of your decision, that how eventually what performance you will get. You make one bad decision and you will see that network is behaving very poorly. So these decisions are a result of your research, and then we go to the 3GPP, and then the companies need to agree that this solution makes sense or not. So this is how the standardization research work. So again, what are the standardization challenges? First, we need to decide what to standardize and why. What is the reason that, for example, if we're going for this AI/ML algorithms, you're going to the standardization body and you're saying, I want to standardize this signal. So obviously the next question is why you want to do that. So you need to prove that it makes sense to do that. And that is partially based on your performance results, and also based on the logic that why this is key enabler for this whole thing. So then data availability and benchmarking. So maybe your solution is very good, but do you have data for that? And how you will compare your results with something else. So from where the data will come. So that will be standardized before anything is implemented. New KPIs for comparisons. Again, this I said before that AI/ML will bring new KPIs. We never thought about training or inference or any KPI which is related to AI/ML, like these, I think, success probability and training rate, and how many GPUs you need, how many layers, how many neurons. Wireless networks never thought about that. But now you need to communicate to the other party, because the other party may have different version of the same algorithm, one with more layers and the other with less layers. So how you will compare if you don't send these information? So now it's a different comparison. ML algorithm complexity and power constraints. So you could have very good algorithms, but if they take all energy of your device, it's difficult. Stability and adaptability of ML algorithms. So how stable your algorithms? Conventionally, the algorithms we have for wireless networks, they were really stable. So this is one of the key things that we always look, because you don't want your algorithm to fail at a particular place. But with your ML field at this point, I think all of you agree that we don't know that how ML will behave. So it's a black box. So should we really rely on black box when we don't know how our thing is working? So this is one of the key engineering problem that usually in engineering work, we know that how the solution we got. But in AI/ML, if you don't know how you got the result and how it will behave when it is generalized, then it's very difficult. So you really need to make good decisions that which algorithm is really stable for most of the situations. Because these algorithms, there is hardly any math behind them. You just put some data, you train them nicely, but still you don't know. Until we have this explainable AI, this is a key problem for us, because it's very difficult. And I think the same kind of issues you might have with your medical field, that things are not explainable. Scalable solutions, we do have federated learning, but then we have privacy issues. Okay, so what is standardization research in short? So our focus is on practicality of the solution. It's not about the performance all the time. Many solutions, many technologies, they never made it to 3GPP because they were not practical. They were too complex. And this happens with every G. And goal is not always to find the best solution, but a simple and elegant solution that works. That is always the case. Output is measured in terms of valuable patents generated and not publications. So you will not see standardization researchers doing a lot of publications. Actually, we are prohibited unless we really want to tell the world that this is important and everyone should know it. Usually the focus is much more on the patents. And IPRs generates revenue for companies. This is our bread and butter. So that is why they are important. And now, just before I end, the final word is that AI is an enabler, is a reality. And it is already there. AI/ML activities are gaining momentum in 3GPP, and that I have comprehensively shown in my slides, that we took 5 years to study something, and now this is the right time that we have started doing specification work. And the first specification for this AI/ML 6G will be available, I guess, in a few months, next year at some point. And 6G will be the first generation with this AI/ML at the heart of the technology, because we are working on this from last 5 years. We will work more for 5 years. And now when we started working on this, we already knew that we have to build the systems which are based on AI/ML, which was never the case for any previous technology. But that's the end of my talk. Thank you for listening.
Learn a lot about 6G network. So we're kind of running a little bit late. Maybe just a couple questions from the audience. Hello, hello. Okay, that works. Any questions from audience?
There's a couple questions that were
I say online. There's a one
in the chat
online
here.
question.
So if you wanted to answer the questions here.
Okay.
If you could just read them out.
Okay, so maybe one question from David.
Yeah, I could read them too. So the first one is, will 6G require training data right at the network edge, or will the beamforming be trained in a centralized location and deployed to the edges?
So I don't know what does it mean by edge, because we have two edges. So one is on the UE side and the other is on the network side. So first thing is that it's not about 6G training. So as I already showed, that it is about each use case. Sometimes you will do it on the UE side, sometimes you will do it on the network side. And that is something we have to figure it out for each use case. And there is no umbrella kind of answer to that we will do it here or there. For each use case, you have to evaluate that where it makes sense, because where the data is. If all the data is on the UE side, then obviously it makes more sense that you do it on the UE side. But at the same time, UEs are energy limited. So then what to do? So there is no single answer for 160.
Okay, any maybe one more questions? Any audience? Okay. Yeah, is there another online question here?
Yeah, maybe if you scroll all the way down, if we go down to the bottom one. So you talked a lot about 6G using AI, but you didn't talk about any like changes to the actual RF modems being used. Is there an expectation that there will still be changes to the RF or radio hardware being used, especially in end devices?
Yes. But again, here what I talked about, it was more about what you need to run those algorithms as over the air interface. What you need to do on the device side, so that is the device vendor's problem. Because they have to train the algorithm, they have to provide these inference results. So whatever they are doing in the whatever will be needed, they have to do that. And most likely they will need to do that, because with conventional CPUs, probably we cannot do AI.
Okay, I think, thank you very much. Yeah, for this excellent presentation. And if for someone after the talk and join the speaker for dinner, yeah, let us know. Okay.
Thank you very much.
Can I have a big round of applause for our speaker? Thank you.